Hi, I am Sandeep Jain, mentor of this DSA self-paced course. I am here for complete clarity on the course. Now the most important question, how do we learn DSA? For this, I offer you my years of experience combined with knowledge in the form of this course. Now the last question, are you ready to invest in yourself? Before we begin our data structures and algorithm journey, let's talk about analysis of algorithms. Analysis of algorithms is super important before we start writing algorithms or before we start learning data structures. Why is it important? For a given problem, there can be multiple solutions, and these multiple solutions might be using different algorithm techniques, might be using different data structures. How do you decide as a programmer which one is better? And this is where analysis of algorithm plays an important role. So we are going to discuss this problem where we are given a number n and our task is to find sum of first n natural numbers. Right? For example, if n is 3, then our output is going to be 6. How do we get 6? 1 plus 2 plus 3. We need to find sum of first n natural numbers. If n is 5, then our output is going to be 15. 1 plus 2 plus 3 plus 4 plus 5. See, in this video, I have written complete input and output. In the upcoming videos, to save writing too much text on the board, I am going to use IP for input and OP for output, right? Just to save the space here. So we have an input number n. We need to write a function that returns sum of first and natural numbers. Please pause this video and try to write down a function yourself. We are going to discuss 3 different solutions of this problem, and then we are going to compare these 3 different solutions. Here are 3 different solutions written by 3 different programmers, and your solution very likely might be matching one of these 3 solutions. The first programmer has simply returned n into n plus 1 by 2. It simply uses the formula, right? If n is 3, we are going to return 3 into 4 by 2, which means 6, right? The second programmer implemented the loop logic. What this programmer did, initialize the sum as 0, then 1 by 1 added all the natural numbers. First added I equal to 1, then 2, then 3. So this is how you get sum of 3 natural numbers. If n is 4, then the programmer is going to run the loop for till 4 and it's going to add 1, 2, 3, 4, right? So this is how the idea of second programmer is. The third programmer, what it did, it used nested loops, one loop inside the other. And what happens here, the programmer runs a loop from 1 to n, right? And then runs a loop from j equal to 1 to I. And for every iteration of the inner loop, it does sum plus plus. So what it is doing, it is having sum as 0. Then for the one iteration of the outer loop, the inner loop will run once only, right? So it will add 1 to the sum, right? So sum will be getting 1 added. Then when the next iteration of the outer loop comes, the outer loop runs for I equal to 2. And for I equal to 2, the inner loop runs 2 times for j equal to 1 and j equal to 2. So sum gets added 1, 2 times. And in the third iteration, 1 is added 3 times, right? We do sum plus plus means we add 1 to sum, right? So this is how we get again sum equal to 1 plus 2 plus 3, and we get the result as 6. So this programmer is actually adding 1 n into n plus 1 by 2 times to sum, and this is how this programmer is getting the sum. So these 3 functions give you the correct output. Now the question arises, which of these 3 functions is going to take the least time? Which of these is most efficient? See, when you talk about time taken by a program, it depends upon many factors. It depends upon the computer on which you are running. Suppose you write an inefficient program to solve, say, this natural number sum problem, and you run it on a very fast machine. Then your inefficient program might take less time compared to the other efficient program that you've written and run on a slow machine, right? The one factor is machine, processing power of the machine. The other factor is programming language. See, programming languages like C and C++ are compiled languages, and Java and Python are interpreted. So what happens in C and C++, when you generate the binary, it's specific to your machine and the binary runs on your machine. It's native to your machine. But when you write Java and Python codes, the code that is typically generated is intermediate code, and it's interpreted. It's run line by line by the interpreter. That's why the Java and Python programs typically run slower. So it depends upon the programming language also. If you have written in C and C++, it's likely to take less time compared to Java and Python. Even if you write these three functions in same programming language and you run on the same system, you might not be exactly able to figure out which one is more efficient due to reasons like system load. Say when you are running an efficient code, right, the most efficient of these three, at that moment what happened was your system was running a background upgrade. It was loaded. So what might happen is your system might take more time for an efficient solution. Now comes one more very important problem. Say you and your friend, you both wrote different solutions to solve a problem. For certain inputs, say your friend's solution is more efficient, and certain other inputs, your solution is more efficient. Now, how do you figure out which one is more efficient? Because for certain inputs, his solution is taking less time, and for certain inputs, your solution is taking less time. To overcome all these problems, all the problems that I've discussed so far, we have a solution called asymptotic analysis, which is a theoretical and mathematical analysis. With asymptotic analysis, we don't even have to implement all the solutions. By looking at the algorithms, by looking at the solutions, we can tell which one is more efficient theoretically. Let us now talk about asymptotic analysis. This is the analysis that we do most of the time. Whenever we talk about analysis of algorithms, we talk about asymptotic analysis only. The terms like theta notation, big O notation that you hear a lot, all these terms are related to asymptotic analysis only, and they are called asymptotic notations. The thing about asymptotic analysis is we measure order of growth of time taken by a function or program in terms of input size. For example, if input size is n or input value is n, does your program grow quadratically, linearly, is it constant, or any polynomial function it has, right? We check that part only. How is the time taken growing in terms of input size? That's what we measure in asymptotic analysis. We'll get a very clear idea when we'll do some examples. The thing about asymptotic analysis, the best part about asymptotic analysis is does not depend upon the programming language, does not depend upon the machine, and does not depend upon the test cases also. We talk about worst case analysis most of the time, and that's algorithm specific, not test case specific. One more thing about asymptotic analysis, you don't have to implement the algorithms, right? You have an idea, you write the steps, then you can analyze it. Is it worth implementing it, right? You don't have to implement like we implemented 3 different approaches. We could just write the idea of 3 different approaches or write the algorithms for 3 different approaches, and we could analyze them using asymptotic analysis. We do not have to implement and then measure the time. Let's now get an idea about asymptotic analysis. So what we do in asymptotic analysis is, the first thing that we do is we get an expression of time taken by your code in terms of input size. So let's understand this with the same examples that we wrote earlier. This is a first way of writing the code to find the sum of first and natural numbers. We are using a direct formula here. So what are we doing in this function is, we are doing an addition, we are doing a multiplication, and then we are doing a division, right? So if you consider these 3 operations independently, you are basically doing 3 operations. And we always assume that a mathematical operation or a comparison operation or any type of operation always takes constant time irrespective of input value. Whether you add 1 million to 1 million or you add 10 to 1 or 5 to 1, they are assumed to be taking the same time in asymptotic analysis, right? So what we are saying is we are doing 3 operations, and all these 3 operations take the constant time irrespective of input value. So that is why we have written the time taken as C1 here. Let's now see the second function. In this function, we are running a loop from 1 to n, and then we are doing sum equal to sum plus I. So this expression is happening n times, right? And then there are certain expressions that are happening only once. For example, this sum equal to 0 is happening once, this initialization of I equal to 1 is happening only once, this return sum is happening once. So there are some things which are being executed constant number of times and some things which are being executed n times. So that is why we have written the time taken as C2n plus C3. Now one interesting thing is, even if it is not exactly n times, even if I write this as say less than n or say less than n minus 5, even in those cases I can write the time taken as C2n plus C3. Why? Because say if I write n minus 5 times with some C1 and then say some C2, I can rewrite this as with new constants say C6 and C7, then I can write as C6 n plus C7, right? Now C6 is same as C1 and C7 is C2 minus 5C1, right? So even if you have less than sign or you have n by 2, n by 3, it's all can be written as C2n plus C3. If you have n by 2 or n by 3, then your C6 becomes C1 by 2, right? So as long as you have an expression in terms of n here, you can always use C2n plus C3 for such loops, right? So this function is going to take this much time. Let's now see our third example. In this example, we have this expression which is being executed n into n plus 1 by 2. What are we doing in this logic? We are incrementing sum these many times. So we are ultimately getting the same value here, right? So if I try to compute how many times this expression is being evaluated, I get n square by 2 plus n by 2, right? This is what I get. So those many times this expression is being evaluated, and then there are some other expressions which are being evaluated different number of times. For example, this is being evaluated once. So this is also being evaluated once. This is being evaluated n times, right? Because this j equal to 1 initialization happens for every value of I. So overall, I can write it as C4n square plus C5n plus C6. There are certain things which are happening constant, which are taking constant time. Certain things which are happening quadratic, certain things which are happening linear number of times. So that's the expression for time taken by this function fun3. So we got expressions of time taken for all three functions, fun1, fun1 and fun2 and fun3. See here I have written the time taken for actual implementations. I have written the codes which work in C, C++ and Java, all the languages. But we don't have to implement. We can write the algorithm also and analyze the algorithm as well, right? Now, time taken we got in these forms. Let's get an idea of order of growth as well. So how are these time taken helpful to figure out order of growth? See, to give you a quick answer, what are we going to do in the order of growth is, we are simply going to take the leading term of every expression. We are going to say it's constant order of growth, does not depend upon n, it's linear and it's quadratic, right? We'll talk about formal definition of order of growth and how did I say constant, linear and quadratic later. But a simple rule is you can always ignore the lower order terms, right? And you can say this is what the order of growth is. For example, here there are three terms, I can ignore these two and I can say it's quadratic, right? That's the simple idea. We'll talk about that later. Let's now get the understanding of order of growth, how these expressions help us. So let's take some example values. Let's say you are the one who wrote this efficient code and your friend wrote this inefficient code, right? And you ran it on a machine where the value of C1 is 13, right? You ran it on a say slow machine where it takes 13 units of time to do this work, this constant amount of work, or you can say C1 is 13 for your machine, right? Now your friend ran it on a different machine which is slightly faster, and for him say C2 is 2 and C3 is 5, right? So your friend got the expression 2n plus 5 for time taken and you have the expression as 13, right? So what happens with these two machines and these two functions when you run them, and I'm assuming that every time you run them they are going to have the same constants, the machine load does not change, right? So what happens in time taken is your machine's time is always going to be 13, right? It's constant value. Fun1, your function, it's always going to take 13 units of time on your machine. Your friend's time taken depends upon n. So it's going to be taking for n equal to 1, it's going to take 7. For n equal to 0, it's going to take 5. For n equal to 3, you can put the value and you can get. And if I find the intersection point of these two functions, I can get the intersection point as 4, right? 13 equal to 2n plus 5, and I get the n as 4, right? So this is what the value of this intersection point is. Now if you take a look at this intersection point, what happens is, after this intersection point, your friend's function is always going to take the more time, right? Even if your friend chose a faster machine, had a faster machine than you, and you had written your code fast but your machine was slower, but after value of 4, your friend's code is always going to take more time than you. That's the beauty of order of growth. Because the order of growth of this function is higher and this function is lower, it's constant and it's linear, right? The machine specific things go away, right, after the value of 4. Now, even if you choose a further slower machine, say you have n equal to 1000 and your friend has even lower values, even in those cases, there would be a value of n after which this expression, because this is growing with n, right, and this is constant. So there would be a value of n after which this expression will have more value than your value. Here I have redrawn the graph for different constant values. Say this time you got even a slower machine. You had to run your logic, your fun1 function that you wrote on a mobile phone, and your friend got even a faster machine. So the constants for you are 1000 and constant for your friends are say 1 and 1. So the value of the function fun2, the time taken for fun2 is n plus 1, because the friend is running on even a faster machine. And for you it's only it's high value, it's 1000, right? You got a mobile phone now. Now your friend says that my program is taking less time. Now how do you prove that your program is faster? So the asymptotic analysis works here as well. What is going to happen is there is going to be a value of n after which your friend's program is always going to take more time. It's just that the value of n is higher this time because you have a slower machine, your friend has a faster machine. So if I compare these two functions, n plus 1 and 1000, and if I say give me the values for n for which I have higher value of this expression, I get the value of n as 999. After 999, and 999 is this point, after this value, the fun1 is always going to take more time than fun2, right? The fun1 is always going to take more time. You can put the values. It's going to be 1000, 1001, 1002 and 1003 and so on. So that's what the great thing about asymptotic analysis and asymptotic notations are. We are going to see mathematically also why it is true that if something is having higher order of growth, then that thing always have higher value after certain value of n. We'll discuss that, how is it mathematically true. Before we end this video, let's quickly talk about fun3 also. Fun3 is a quadratic function, right? And quadratic functions grow even faster. So quadratic functions grow like this, right? So fun3 is going to have a value again, after which it's going to take more time than even fun1 and fun2. Before we end this video, let's quickly talk about fun3 also. Fun3 is a quadratic function. So it's going to have a graph like this, right? A quadratic growing graph. And you can notice that after a certain point, fun3 is having more time than fun1. And if I compare it with fun2, then the way I've chosen the constants here, drawn the graph here, it's having higher value than fun2 all the time, right? One last thing about asymptotic analysis and this graph, we are always going to be considering this quadrant of the 2D coordinate system, because the time taken by an algorithm cannot be negative, right? It is either 0 or growing with the value of n. And n is typically size of input, right? And this value of size is always going to be 0 or greater than 0. So whenever we draw the graph or whenever we talk about asymptotic functions, asymptotic analysis, see, these are the functions of time taken, right? They show you how much time taken by fun2 and how much time taken by fun1, right? So they are always going to have a value greater than or equal to 0. Same is the case for input size n. So the basic idea of analysis of algorithm, the main idea is to measure order of growth of time taken by algorithms. That's the main idea that we use. However, this has some limitations. If you remember the previous example, when we were comparing 1000 with n plus 1, say an algorithm takes 1000 instructions or 1000 unit of time, and there is another algorithm that takes n plus 1 unit of time. This 1000 may be higher because this is probably implemented in a programming language that takes more time, and maybe it's running on a machine which is slower, but it takes 1000 units of time. And we saw that when n becomes greater than 999, then only this algorithm starts taking less time compared to this algorithm. Now imagine an environment where your n never reaches more than 999. When you were comparing your program, which was constant, with your friend's program, suppose it never happens that input size goes beyond 999, right? So that's a limitation of this order of growth analysis. We always talk about limit n tends to infinity. We always talk about that, right? However, in practically, it might never reach that limit, right? It might never reach that high value 999. But that's what we talk about. We talk about only large input size in this theoretical analysis. That's what everybody does when we analyze algorithms theoretically. Let us now talk about order of growth. Order of growth is the main criteria when we do theoretical analysis of algorithms. The idea is simple. If order of growth of the function which represents time taken by an algorithm is more compared to another algorithm, then we say that this algorithm is a bad algorithm. So Fn if said to be having higher order of growth than Gn, if limit n tends to infinite, Fn divided by Gn becomes infinite. And higher order of growth means we say the algorithm whose time is represented by Fn is a bad algorithm, right? So if Fn represents a bad algorithm, then Fn by Gn for n tends to infinite would be infinite. Or Gn by Fn for n tends to infinite is going to be 0. So I'm going to use this expression here, this expression to prove that order of growth of Fn is higher. I've taken this example, n square plus n plus 5 and 2n plus 5, and I'm going to use this expression to show that Fn is growing faster. And please remember, all this discussion is under these assumptions. First quadrant, right, of 2D coordinate system, where n is 0, n is greater than or equal to 0, and Fn and Gn are also greater than or equal to 0. They are mainly positive functions. So let's compute the value of this expression. Fn divided by Gn divided by Fn when n tends to infinite. So we have 2n plus 5 divided by n square plus n plus 6, and we are talking about limit n tends to infinite. So when we talk about order of growth, we always talk about n tends to infinite, although it might not be a practical idea, as we saw in the previous video when we were talking about fun 1 and fun 2, and we saw that fun 1 was having less value only when n was greater than 999, right? And in practical situation, it might happen that your input never reaches more than this value, right? But that is fine because it's theoretical analysis, and that's what we do here, right? So let's talk about this expression value. The simple idea to compare order of growth of two functions and get the value of this: take the highest order term and divide it by both numerator and denominator. Highest growing term. Highest growing term is n square. So we divide both numerator and denominator by n square, and what do we get? 2 divided by n plus 5 divided by n square divided by 1 plus 1 by n plus 6 by n square. Now when n tends to infinite, what this value is going to be? When you have n in denominator, all those terms are going to be 0 when n tends to infinite, right? So this is going to be 0, this is going to be 0, and this is going to be 1 plus 0 plus 0. So what is this value? This value is 0, right? 0 divided by 1 is equal to 0. So you get the value 0. You get the value of this expression Gn by Fn is 0. And this is the required condition to prove that Fn is growing faster than Gn, right? So order of growth of Fn is faster than Gn. So if Fn represents time complexity of an algorithm and Gn also represents time complexity of another algorithm, then we say Gn is a better algorithm. There is a direct way to compare order of growth of two functions. In fact, there is a direct way to find out order of growth of any function. Under the conditions, when n tends to infinite, and we are talking about first quadrant, n greater than or equal to 0, and that function is also positive. Under these conditions, we can quickly find out order of growth of any function, and we can quickly compare these order of growth. The idea is simple. Given a function, we ignore the lower order terms, we ignore the leading constants. Now, how do we decide which terms are lower order terms? We must kind of remember this thing, that constant is the lowest growing thing. It never actually grows, it remains constant. Log n grows faster than constant, then log n, then n raised to the power 1 by 3, n half, then n square, n cube, n4, 2 raised to the power n, n raised to the power n. These are the commonly seen terms in algorithms. Now we have talked about ignoring lower order constants, ignoring leading constants, and then how do we decide which one is lower? Let's do some examples. Say I have a function f1 whose value is 2n square plus n plus 6, and I have another function gn whose value is 100n plus 3. Now how do you decide which one is better or which one is faster growing? You ignore the lower order terms of both the functions. So from here you can refer n square is higher order term. So you can ignore n here, right? You can ignore 6 here. And you can ignore the leading constant. You can ignore this constant too. So you say that Fn's order of growth is n square. And what about Gn? You can ignore the lower order term, which is a constant. You can ignore leading constant. And you can say Gn order of growth is linear. And now if there are two algorithms and they have these times taken by them, then you definitely say that Gn is better because n is less than n square. The time taken by Gn is going to grow slow when n grows. And we are talking about n tends to infinite. So that's the general idea, the direct way to find out the order of growth. Ignore the lower order terms, ignore the leading constants, and find out the order of growth and simply compare them. And how do you decide which terms are lower order? You can use this. And the same thing you use to decide which is having better order of growth in these finally found order of growths. Let us do some exercise to find out order of growths of functions and compare them. Say you have Fn as c1 log n plus c2 and Gn as c3n plus c4 log n plus c5. These c1, c2, c3, c4, c5, they are machine specific constants, right? So they are doing some addition, subtraction in your algorithm and we just put the constants in place of them. Now, which one is growing faster? Please pause this video, find out the order of growth of both the functions, then compare them. So you can ignore the lower order terms in here. C2 can be ignored. Leading constant can be ignored. So you get the order of growth as log n. Which one is lower order term here? This one, because this comes before n. So you can ignore it. You can ignore it. And you can ignore the leading constant. So the order of growth of this function is n. Now, which algorithm is better? This algorithm or this algorithm? So this algorithm is definitely better because its order of growth is less. It grows logarithmically. Let us do one more exercise. C1n square plus C3 plus C4 C5 n log n plus C6 plus C7. What is the order of growth of this function? We ignore the lower order terms, ignore the leading constant, we get n square. What is the order of growth of this function? Ignore the lower order terms, ignore the leading constant, n log n. Now which one is faster or which one is having less order of growth? See, we can simply cancel one n with the other n and we get here n extra, and here we get log n extra. So n is definitely more from this and this. So we say this algorithm is faster, right? It's going to grow slow, and we can say order of growth of this algorithm is more, right? So this algorithm should be preferred in when you have two algorithms with these times. Let's now talk about average, worst and best cases of algorithms. Before we talk about that, let's take a closer look at this example function. What are we doing in this function? We have written a function that takes an array as input, size of array as another input, initializes the sum of array elements as 0, then traverses through array elements and computes the sum, right? So this function is basically doing the array element sum and returning the sum. Please pause this video and try to guess the order of growth of this function. The time taken by this function is clearly C1n plus C2. There are certain things that we are doing constant number of times, like this initialization, and returning sum at the end. And then there are certain things that we are doing linear number of times, like this statement is being executed linear number of times. This condition is being checked linear number of times. This increment is happening linear number of times. So we have C1n plus C2, right? And order of growth can be easily seen as n. Now please see this example 2 and try to guess the order of growth of it. See, due to some business reason, what we have here is if the user provides even sized array, we return the sum as 0. Otherwise, if the user provides odd sized array, then we do the actual array sum and return the sum at the end. Right? Now if I ask you about order of growth, you can't make a general statement. You can't say that the order of growth is constant or linear, because it depends upon the type of input. If user input is even sized, then it's going to take the constant time. If the user input is odd sized, then it's going to take the linear time. So what we do in algorithms is we divide all cases into 3 cases for algorithms, and those 3 cases are best case, average case and worst case. Now what is best case? You must have guessed it. What is the minimum order of growth of an algorithm? For example, in this algorithm, the best case happens when user provides an even sized array. And in this case, our time taken or order of growth of this algorithm is constant, right? So the best case complexity or the best case thing for this algorithm is constant. Now, what is average case? See, average case goes like this. It's like time taken for every input. Say you know that you've written this function and users of this function are going to provide these 1000 different inputs. You compute the order of growth or time taken for every input, right? Those 1000 inputs, and then divide the sum by 1000. Like it's just like doing the normal average thing. So many times we don't know what 1000 inputs user are going to provide. So we make some assumptions. And what assumption I have made here is, I have made this assumption that user is going to provide half of the time even input and half of the time odd input. I have written that under the assumption that even and odd are equally likely. So what is going to happen here? It's going to be linear in half of the cases when the user provides odd sized input array, and it's going to be constant in rest half of the cases when user provides even sized input array. And if I do the sum of these two and divide it by 2, right, I am going to get something like C1n by 2 plus C2 divided by 2 plus C3 divided by 2. So C1, C2, C3 are some constants. We can ignore them. These are lower order terms. We can ignore the constants of the leading term as well. So we get n again. So the order of growth in average case is linear. But average case is something which requires you to make certain assumptions about the input, or in ideal situation requires you to know the exact input and then compute the average. That's why average case is not typically done. Although we would like to know what is the time taken in the average case, but we can't do it many times because we don't know how user is going to use this particular function, what is going to be the distribution, what are going to be the inputs. We don't know those things. Talking about the best case, see, best case is also not used. If you are building a software and if you tell your user in the best case, my software is going to respond in 0.001 microsecond, but I don't know about the worst case or average case, it might take hours. Nobody is going to buy your software, right? So we do not provide much information when we mention the best case of an algorithm, right? Worst case is something that we use most of the time. We find out what is the input case for which it's going to take the maximum time, or it is going to have maximum order of growth. And here it is clear that if user provides odd sized array, then it's going to take the maximum time, or it's going to have the maximum order of growth, and that order of growth is linear, right? So the worst case of this algorithm is linear. To summarize the worst case, average case and best cases, see, many times when you write program, if your program does not have any condition that it's going to have different orders of growth or different cases, you can simply say one line of the order about the order of growth, and you can say that's what the order of growth is. For example, the example one where we were doing the simple sum of the array elements. Other real world example can be, for example, you want to find out the maximum in an array. In that case, you will have to traverse the array to find the maximum, right? There is no best case, no worst case, no average case, right? It's like always going to be linear. And similarly, minimum in an array, right? It's always going to be linear. But many algorithms, they have different cases. For certain input, they take different time, and for certain other input, they take different other times. And there are many standard algorithms also like this. There is insertion sort algorithm. If you provide sorted input, it takes linear time. If you provide reverse sorted input, it takes quadratic time. So the cases when your algorithm has different times for different types of inputs, in those cases we divide the cases into three cases: best, average and worst. Best is something which is bogus. We don't require the best case. Saying that its minimum time is this is of no use. Average is something we would like to know but impractical many times. And worst case time complexity analysis or worst case asymptotic analysis is something that we do most of the time. We find out what are the input types when this algorithm is going to have maximum order of growth. We use that order of growth most of the time to indicate it as time complexity of the algorithm. Let's now talk about asymptotic notations. Asymptotic notations are the mathematical notations to represent order of growth of any mathematical function. There are mainly three popular asymptotic notations: big O, which represents exact or upper bound on order of growth; then theta, which represents exact order of growth; then omega, that represents exact or lower bound. So why do we need exact or upper? Why do we need exact or lower? Say if I have a function c1n plus c2, I can ignore the lower order terms, right? I can ignore the constant. I can say that order of growth is n, right? And if I take another example, say if I have c1 n square plus c2 log n plus c3, right? I can always tell you the exact order of growth. I can ignore the lower order term, I can ignore the lower order term, ignore the constant. I can say order of growth is n square, right? So I can always use theta notation, or I can always tell the exact order of growth. Why do we need big O notation, which is exact or upper, or omega notation, which is exact or lower? Let's understand it with an example. Say this is a linear search code, and this example is similar to the examples that we discussed in the previous video, where we talked about in certain cases we were taking constant time, in certain cases we were having linear time, when we talked about that getSum function, modified that getSum function. So the same thing happens here. If you talk about linear search, and say if you have this array, and say if you are searching for an element x, right? This function, what it does, it takes an array, size of the array, and an element to be searched in the array, traverses through the array. As soon as it finds a match, it returns the index of that match, and if it does not find any match after traversing the whole array, it returns -1. So say you are searching for 10 only. So what will happen in this case? It will find the 10 at the first place. It will return immediately. So it's taking only constant time when the element is present at the first location. And when the element is not present at all, then it's going to traverse through the whole array, right? It's going to come out of the loop, it's going to return -1. For example, if you search something like 75, right, it's going to traverse till this point and then it's going to realize element is not present, it's going to return -1. So in the worst case, it's going to do linear time. Now if I want to say anything about order of growth of this function, I'll have to say something like this. Say in the best case, it takes constant time. In the worst case, it takes linear time. And if I just want to say this thing in one line, or say I don't want to evaluate the best case, right, evaluate other cases, I just evaluate the worst case. And what I say is, I say this algorithm takes big O of n time, right? Big O of n means it's either linear or less than linear. As I said, it represents exact or upper bound. So if you have a function which is c1n plus c2, you can write it as big O of n. Mathematically, you can write it as big O of n square also, right? Because any upper order of growth can also be written in big O notation, right? You can write anything higher than n, right? Not less than n. You can write either n in big O notation, or you can write anything higher than n. You can write n log n, n cube, n4, or anything. So the point is, if I say that this algorithm is big O of n, what it means is, it means either it takes linear time or takes less than linear time. So with big O notation, I can talk about this time taken of this algorithm in one line. We'll be discussing big O notation, theta notation, omega notations in separate videos in detail. The idea here is to introduce these three notations. Big O means exact or upper. For this algorithm, I can say it's big O of n. Theta means exact. For this algorithm, I can't represent the time complexity using theta notation in one line. If I use theta notation, then I'll say this algorithm takes theta n in the worst case, right? That's what I can say about this algorithm, because in the worst case, when an element is not present, it has to traverse after the till the end, and then it has to realize that element is not present, right? So in the worst case, it's theta n, right? I'll have to use the word worst case when I'm using theta notation. Omega notation is opposite of big O notation. It represents lower bound or exact bound. So if you talk about this function, see, in the best case, it's going to take constant time. And constants, when we talk about big O and theta, theta 1 represents constant and big O 1 also represents constant. When you write theta 1 and big O 1, we mean that constant. Right? We'll discuss these things, these notations in detail when we talk about big O and theta. But big O1, theta 1 means constant. With any notation that you write 1, it means a constant value. See, omega 1, since it's exact or lower, what it means is it's either constant or any value higher than constant. So big omega 1 or omega 1, it represents a constant value or any value higher than constant. So if you have a function c1n plus c2, you can write this either as omega of n, that will be like exact bound, because exact bound is there in both big O and omega. So I can write it as omega of 1, right? Omega of n. This is how we write the omega notation, and I can also write it as omega of 1. This is also mathematically fine because omega means lower as well. So what I do is, I write the time complexity of this algorithm is omega 1, right? And when I say omega 1, it means either constant or any value higher than constant, which means this covers all the cases. So we are saying it takes constant time or higher than constant. That's what we mean by omega 1 or constant, right? And when we say big O of n, that means it takes either linear time or less than linear time. Here what are we saying? It takes either constant time or higher than constant time. But which one you would prefer? See, as we have discussed in the best case, average case and worst case, we are most of the time interested in an upper bound, right? That's why omega notation is not used much. You would rarely see omega notation in analysis of algorithms. Most of the time you would be seeing big O notation and theta notation, because theta notation gives you an exact bound and big O notation gives you an upper bound, and you're most of the time interested in either knowing the exact bound or knowing the upper bound. Let's now talk about big O notation. As we have discussed earlier, big O notation is used to represent exact or upper bound on order of growth. Please note that if you know the exact bound, you would prefer to use theta notation. That gives you more information. This is what exact bound is. So main use of big O notation is when you want to represent an upper bound, right? When you have an upper bound, you use big O notation to represent the upper bound. So there is a direct way of finding the big O notation for an expression, and the direct way is just to find the order of growth, and since exact is there in big O, you write the order of growth in big O notation. So these are the steps that we use to find the order of growth also. So if you see this expression, the order of growth is clearly n square. We ignore the lower order terms, we ignore the leading constant, and we get the order of growth is n square. And since big O notation covers exact or has upper bound, we can write it as big O of n square, right? Mathematically, you can write it as big O of n cube also, n4 also, anything higher, because big O of something means that thing is order of growth wise greater or equal, right? So we are writing equal here. When we know that's equal, why to write an upper bound, right? Why to write a higher value? So in this expression, this is a lower order term because we have n log n here, right? N log n is a higher order term. We ignore the lower order terms, we ignore the leading constant. So we have the order of growth as big O of n log n, right? Let's now see this expression. Here we ignore the lower order terms, we ignore the leading constant, and we have order of growth as big O of n cube. So this is a direct way of finding order of growth. Now you see mathematical representation of big O notation. How do we mathematically see big O notation? Let's now talk about mathematical definition of big O notation. Please remember one thing, whenever we talk about asymptotic analysis, asymptotic notations, we talk about values of n tends to infinite, large values of n, and that's what you would notice in this definition also. We have n greater than equal to n naught. So we are talking about all the values greater than a certain constant value n naught. For those values, this condition should be true. Fn should be smaller than or equal to c of gn. Then we say Fn is big O of gn, right? So for example, if you have Fn is 2n plus 3, you would say it's big O of n. So what is gn here? Gn is n, right? You would say it's big O of n only when there exists a constant c such that 2n plus 3 is smaller than or equal to cn for all n greater than or equal to n naught. We just need to figure out these two values, c and n naught, and we need to show this thing. Then we can say this is equal to big O of n. And we have learned in the direct way that we have this as big O of n, right? We can ignore the lower order terms, we can ignore the leading constant, we can quickly say it's big O of n. Here the intention is to just to show you mathematically also, right? How does this work? So we have gn as n and we have fn as 2n plus 3. Now we need to find out two values, c and n naught, and we need to show that this is always true after values of n greater than or equal to n naught. For that purpose, I have taken c as 3. Now you might be having a question, how did I pick 3? See, what you can do is, you can always take the constant of the highest growing term, which is n here, right? And just add 1 to it, right? To prove that this is big O of n, you just add 1 to it. So now you get 3, right? So your c is 3, and you need to show that 2n plus 3 is more than or equal to 3n for all values of n greater than certain value. And that certain value can be figured out by just simplifying the inequality. We have 3 smaller than or equal to n now. So n naught becomes 3. N naught is 3 and c is also 3, right? You can notice that after value 3, this value 3n is either greater or equal. See, if you see 3 itself, they are same at 3. This is 6 plus 3, 9. This is 9. Now if you take 4, this is 4 into 2, 8 plus 3, 11, and this is 12, right? For all the higher values, this term is going to be greater. See, why does this work that we always take just one higher value? Because it's the higher growing term, right? This is the highest growing term among all the terms. We have 2 terms here and it's the highest growing term. So if you keep on increasing the value of n, it will dominate over other terms. And if you have a higher multiplier, this is definitely going to give you higher values after a certain value. Let's now see more examples of big O notation. So here I have written constant values. any constant value can be written as big O of 1. For example, 100, log 2000, 10 to the power 4, 10 to the power 8, 10 to the power 10. All these are big O of 1. As long as the value is not dependent upon n, there is no n in the term, we can write these values as big O of 1. Here are examples of big O of n. And please note that I have U here. U means union. See, big O notation means exact order of growth or higher order of growth. So we can cover these terms also. These both terms come under big O of n, right? So constant also can be written as big O of n, but ideally you would not write them as big O of n. You would write them as big O of 1. When you know that it's exact constant growth, you would write big O of 1 notation. And in fact, you would not use big O notation for those purposes. You would use theta notation, right? Ideally, you would use theta notation when you know the exact order of growth. So here are examples: n by 4 to n plus 3. If you ignore the lower order term, ignore the leading term constant, you will get these order of growth as big O of n, right? Now this is a lower growing term. This is log n, and log n is smaller growth than n. Still we can write it as big O of n, but ideally we would write it as big O of log n, or even better would be theta log n. When we know exact order of growth, we would write using theta notation, not big O notation. These are just to explain you mathematically. So let's see this example. In this series, we have all the terms that have order of growth of as n square, and we can write all of these as big O of n square. And we can write these also as big O of n square. But again, ideally, you would like to write the exact order of growth. You would like to write this as big O of n or theta of n. This as theta of log n or big O of log n. Big O notation works for multiple input variables also. For example, if you have 100 n square plus 1000 m and n are two input variables, what we do in this case, we again take the highest growing terms. So n square is the highest growing term. Then for m, this m is the highest growing term. So we write n square plus m as the order of growth. Let's see this example. M square is the highest growing term for m, right? For n, we have two terms, n and mn, and mn is obviously the higher growing term, right? It's multiplied with an input variable. We talk about m tends to infinite, n tends to infinite. So we have m square plus mn as order of growth of this expression. Let's now talk about applications of big O notation. Please remember one thing. Whenever we have exact bound, whenever we know the exact bound on order of growth, we should prefer to use theta notation. Why to use a notation which gives you a loose information? Say if you have an algorithm like finding maximum in an array, right? You know that whatever input you provide, you are going to traverse through the whole array, right? And you are going to find the maximum by traversing through the whole array. So it's always going to take n order of growth. So why to use big O notation? Why to say big O of n? You can better say it's theta n algorithm to find the maximum in an array or minimum in an array. But many times you have complex logics, right? When you are implementing algorithms or when you are writing some business logic, you have complex inputs which has many if-else conditions, many termination conditions. In those cases, what you do is you try to figure out the innermost statement, the statement which is being executed maximum number of times. You find an order of growth on the number of times the statement is being executed, and then you say that's the order of growth of this algorithm in terms of big O. Basically, you consider the worst case of the algorithm, right? And in the worst case, you find the order of growth and you put it in big O notation, and then you say this is the time complexity. So you have put an upper bound. It's easy for you to get an upper bound many times rather than knowing the exact bound. Let's take an example to get an idea. Here is an example of a function that checks whether a number is prime or not. So the syntax that I have written here, it's close to C, C++ and Java. The only difference in Java is you will use boolean instead of bool. So this function, what it does, it checks whether a number is prime or not, and we are going to discuss detailed working of this function in the mathematical track where we have discussed prime number checking video, right? We are going to discuss in detail how this function actually works. The idea here is to understand an application of big O notation with the example of this function. See what this function does, it checks whether n is 1 or n is 2 or n is 3. These are the corner cases. If n is 1, it returns false. 1 is not a prime number. If n is 2 or 3, then it returns true. They are prime numbers. Now it again has one optimization. If n is a multiple of 2 or n is a multiple of 3, then also it immediately returns false. So if you provide a number like 100, 200, 500, which is an even number, it will immediately return, right? Or if you provide a number which is a multiple of 3, then also it will immediately return, right? It would not go inside the loop. For other numbers, it will go inside the loop and it will go till square root of n. We have the condition I into I is more than equal to n, which means I is more than equal to square root of n. We'll discuss this logic in detail in the prime number video. And what we are doing I equal to I plus 6. So what is happening here? There might be many situations where we do not run till square root of n. For example, if you talk about the number 65, right? Square root of 65 is going to be above than 8, right? Something beyond 8, right? 8 into 8 is 64. Now, but what will happen here? In the first iteration itself, you will return false because 65 is a multiple of 5. So you're taking constant time. But in the worst case, when your input number is a square of a prime number, in those cases, this will run till square root of n, right? So you are going to run square root of n minus 5 divided by 6 times kind of thing, right? Because it begins with 5, then goes till square root of n and then increments by 6. But we can ignore the constants, we can ignore the lower order terms, and we can say it's square root of n order of growth, right? That's what we can say. Now, square root of n is not always taken. It's taken only when your input is a square of a prime number. For example, 49. It's a square of 7. In only those cases, you will have this loop running a square root of n times. So what do we say about the order of growth of this function? There are many corner cases where it stops well before square root of n, right? So we can use big O notation in such situations. We can say the time complexity of this algorithm is big O of square root of n. That covers everything, right? When you say square root of n and when you use big O notation, it means it is either square root of n or less than square root of n. That covers the constant, that covers divisible by 2 cases, divisible by 3 cases, that covers even the cases when numbers like 65 are provided. So big O notation is useful when you have an upper bound. It's also useful when you have a complex logic and you don't know exact upper bound also, but you can approximate the upper bound by ignoring certain things. We'll discuss as examples when we'll talk about recursion analysis. But the idea is big O notation, whenever you don't know the exact bound, you can somehow figure out the upper bound, you use big O notation for those purposes. Also, in general, what you do is you have an algorithm, you find the worst case, you find the order of growth in the worst case, and you put it in big O notation and you say this is the time complexity of this algorithm. Let's now talk about omega notation or big omega notation. This is opposite of big O. Big O notation is mainly used when you have an upper bound, and big omega notation is mainly used when you have a lower bound. Let's consider an example to understand application of omega notation or big omega notation. Consider a situation where you have an algorithm to implement an online game, and say there are n players in the game, and this game keeps on running forever until unless a player quits the game. If a player quits the game, then the game is over. Now you can't say anything about upper bound on the time taken by the algorithm or program because it keeps on running, but you can have a lower bound. Suppose your algorithm is initializing scores of n players, then you can say the time complexity of this algorithm or this program is big omega of n. It's going to take at least big omega of n time because there might be running a loop which is initializing scores of n people, right? So it's going to take at least linear time and we don't know the upper bound, right? So big omega notation is useful when you have a lower bound. Consider another example where you are supposed to print permutations of a string. So if you have a string with say 3 characters, then there are going to be 6 permutations. In general, there are factorial n permutations. Whatever algorithm you write, it's going to print those factorial n permutations, right? So you can say the algorithm for printing permutations is going to take big omega of factorial n time, right? Because it's going to generate and print all these permutations on the screen, and there are factorial n permutations, so you need at least this much time. So whenever we use big omega notation, we use it to indicate a lower bound on the time taken. If you take a closer look at this mathematical definition of big omega notation, it's opposite of big O notation. It says that Fn is big omega of Gn if and only if there exists constant C where C is greater than 0. See, this condition C is greater than 0 is there in big O notation also. And n naught where n naught is greater than or equal to 0. And we discussed in asymptotic analysis video, whenever we talk about functions, we always talk about this first quadrant where n is greater than or equal to 0 and Fn and Gn are also greater than or equal to 0. So this condition applies everywhere whenever you talk about asymptotic notations or asymptotic analysis, such that Cgn is smaller than or equal to Fn. So this is just opposite. What we were saying in the big O notation, we were saying Cgn is greater than or equal to Fn. Here we are saying Cgn is smaller than or equal to Fn. That's the only difference. And this part is also same for all n greater than n naught. See, this part is going to be everywhere. We talk about always large values of n when n tends to infinite. So if we find a value n naught after which this condition is true, then we use the particular notation big omega or big O. Let's take the same example. Let's say we have Fn equal to 2n plus 3. And please remember, for big omega notation also we can use the direct method. What we do, we ignore the lower order terms, we ignore the constant of the highest growing term, and we say this is big omega notation, because big omega also means equal or lower. So if you see this example, you can ignore 3, you can ignore this constant, and you can say big omega of n. But you can also write it as big omega of 1 or big omega of log n, because smaller values, smaller growing terms are also fine with the big omega mathematically. But when you know the exact bound, why to use smaller bounds, right? The same reason as big O. Let's take some more examples. For example, if you have 5n square plus 4n plus 6, you can simply ignore the lower order terms, ignore the constant of the highest growing term, and you can say it's omega of n square, big omega of n square or omega of n square. See, order of growth is n square for this expression. You can either use big O, you can use omega, or you can use theta when you know the exact order of growth, right? So this is clearly big omega of n square. However, you can write it as big omega of n also, right? Similarly, you can write it as big omega, big O of n cube also. In big O, you can write higher growing. In big omega, you can write lower growing terms. Okay, so this is the direct method, right? We can directly say it's big omega of n. Let's see how does this formula valid here. So we take C equal to n. See, what we were doing in big O, we were taking the constant of the highest or growing term, which is n here, and we were taking one larger value. Here I've taken one smaller value, right? Because when n tends to infinite, this is the term, the leading term is going to be the most dominant term, right? Even if you have larger expression n cube plus n square plus n plus something something, n cube's multiplier or constant would be the most dominant term, right? So we take C equal to 1 here, one smaller value, and we try to figure out n naught. And we get minus 3 greater than or equal to n. And since we talk about first quadrant only, we don't take the negative value. If this is true for all values greater than minus 3, that's going to be true for all values greater than 0 also, right? It's going to be true for minus 3, minus 2, minus 1, 0 and all the upcoming values. So we take n naught as 0. Right, so we have found n naught, we have found C equal to 1, and this formula is valid. So we can say mathematically also that Fn is big omega of n. Before we talk about some more facts about big omega notation, please go back and check the graph that we drew for big omega notation. In the graph, if you notice, C of Gn always has value smaller than Fn, right? For all values of n greater than or equal to 0, right? From 0 itself, C of Gn is smaller. This is opposite of big O, right? In the big O notation, 3n was having greater value than 2n plus 3 after certain value of n naught, and that value was 3. In big O notation video, we saw in the graph. So in the big omega notation, we just need to find an n naught after which C of Gn is smaller or equal, In big O notation, we just need to find a value of n naught after which C of Gn is greater or equal. Let's now see more interesting facts, and these are similar to big O notation facts that we discussed. If you see these terms, these three terms have exact order of growth as n square. So we can say the value of these terms is big O of n square, theta of n square, and big omega n square also. See, exact order of growth is covered by all the notations. Big O covers smaller order of growth also, right? Big O of n square means you have n square order of growth, or you have the terms which have smaller than n square order of growth also. And omega covers greater order of growth also, right? But exact is there in all three, right? So we can write all these three terms as big omega of n square. And with big omega, you can write higher growing terms also. Like this is order of growth n cube, but we can write in big omega of n square. In fact, you can write it as big omega of n and big omega of 1. That's why I have union here. This U means union here, right? So this set, they all can be written as big omega of 1. In fact, any time complexity can be written as big omega of 1. Big omega of 1 means either constant or higher than constant, right? So any algorithm that you have will either have constant time taken or will have higher than constant time taken, right? Let's now see this one. This term has linear order of growth. This one also has linear order of growth. So they all are covered by big omega of n, and big omega n covers these also, equal or higher growing polynomials. These are all constant terms. This is constant, this is constant, this is constant. So they are big omega of 1, right? And big omega of 1 covers everything, right? I have union here. So these are examples of big omega notation. Now, last thing about big omega notation, if Fn is big O of Gn, then Gn is big omega of Fn, right? Because they are opposite of each other. If one function is having order of growth smaller or equal, right, then I can write it here with big omega notation. Let's now talk about theta notation. Theta notation is used to represent exact bound of a function or an algorithm or program. Whenever you know the exact bound, prefer to use theta notation. It gives you the best information. It tells you that's what the order of growth is, right? When you use big O notation, it means either exact or an upper bound. So we use big O notation only when we have an upper bound. When we have exact bound, why not to use theta notation, which gives better information? Omega notation is used to represent a lower bound. So when you have a lower bound, then you use omega notation. Theta is used when you have exact bound on order of growth. Let's see the mathematical definition. We say Fn is theta of Gn if and only if there exist two constants C1, C2 such that C1 is greater than 0, C2 is greater than 0. So if you see, compare this theta notation definition with big O notation, omega notation, it's a combination of both the definitions. In big O notation, we were bounding from this side. In the omega notation, we were bounding from this side, right? And there was one constant in both of them. Since we are combining those two, we have two constants C1 and C2 now. And here also we talk about all values of n greater than n naught, where n naught is greater than or equal to 0. We talk about only this quadrant of the 2D coordinate system, right? N naught greater than 0, equal to 0. And these function values are also greater than or equal to 0 because they represent time taken by an algorithm. So theta notation definition of a function bounds the function from lower side and upper side both. For example, if you see this function 2n plus 3, this is the line represents this function, right? We have seen this in big O notation, right? We found the constant as 3, and we have seen this in omega notation, we found the constant as 1. So in theta notation, we bound the function from both the sides. And bounding the function from both the sides is only possible when you have the same order of growth, right? Because if the order of growth is different, then you can't bound it from the other side, because when n tends to infinite, we talk about n tends to infinite, we'll see the differences. We would not be able to bound both the sides. We will be able to bound only from one side, right? Both side bounding is possible only when your function fn and gn, they have same order of growth, which means the highest growing term is having the same order of growth in both the expressions. Let's see an example. Fn is 2n plus 3. I've taken the same example here, and the same reason we discussed in omega notation. we just take the smaller value constant, right? The smaller value constant of the highest growing term, n is the this 2n is the highest growing term. We have 2, so we take 1. And for C2 we take 3, right? C2 belongs to the theta notation constant and C1 belongs to the omega notation constant, right? So we take 1 and 3, and now we try to figure out n naught. So we have this inequality, right? 2n plus 3 should be greater than or equal to n and should be smaller than or equal to 3n. From this inequality, this part of the inequality, we get n greater than or equal to 3. From this part, we get n greater than or equal to 0. See, we actually get n greater than or equal to minus 3, but we talk about n not greater than or equal to 0 only. So we consider n as greater than or equal to 0, right? Now, if I take a combination of these two, for which values of n, the both will be true. So this is true for n greater than or equal to 0. This is true for n greater than or equal to 3. They both will be true for n greater than or equal to 3. So we have n naught as 3. So we have C1, we have C2, we have n naught. That's why we say it's theta of n. We can use direct method also to find theta notation of an expression. For example, if I have this complex expression, I don't have to find out C1, C2 and n naught. I can use the same method that we discussed in order of growth, because this method gives you order of growth and theta notation represents exact order of growth. So what is order of growth of this? We have discussed it multiple times. We ignore the lower order terms. We ignore this constant and we get n square as order of growth. We can simply put it in theta notation. It's theta n square. Here we can ignore the lower order terms. We can ignore this constant and we can say it's theta of n cube. That's the order of growth of this, and we can simply put order of growth in theta. Here we have log n and n. So this is lower order term. We ignore the constant and we get the order of growth as theta of n. Right? So you can use simple order of growth to get the theta notation, and we can use the same for big O and omega notations also. Let's now see some interesting facts about theta notation. The first fact is, if Fn is theta of Gn, it means Fn can be written as big O of Gn also, big omega of Gn also, right? And Gn can be written as big O of Fn and big omega of Fn. For example, if Fn is 2n square plus n, we can write it as theta n square. And we can also write it as big O of n square. We can also write it as big omega of n square. And similarly, n square can be written as big O of 2n square plus n. Now you might be wondering, what is this big O of 2n square plus n? See, when we write a complex expression in big O notation, this complex expression is actually equivalent to big O of n square only, right? Because again, you can ignore the lower order terms, you can ignore the constant of the leading term, and you can again write it as big O of n square. So you can have complex things inside big O notation or big omega notation, and again the same rules apply, and you can simplify those complex terms, right? So since theta represents exact bound, all these four things are true when Fn is theta of Gn. They both have exact order of growth, right? Fn and Gn, and you can write both of them in all different other four ways. The next thing about theta notation is it represents exact bound, and this is why it is super useful. Whenever you have an algorithm and you know the exact bound, you should always use theta notation. For example, if you talk about maximum in an array, you will always have to traverse through the array. You know that this algorithm is always going to take theta n time. It's good to use theta notation here. If you say big O of n, that kind of does not give you the complete information. It can be n or can be less than n. But if you know it's always n, it's always linear, why not to use theta notation? Similarly, minimum in an array, sum of an array. Even when your algorithm has different time complexities in different cases, it's better to use theta notation. For example, if you talk about insertion sort takes a linear time when your array is sorted, and it takes a quadratic time when array is reverse sorted. So it's better to say, in the best case, insertion sort takes theta n time, because you know it's linear, right? It's not more, not less. It's exactly linear for insertion sort in the best case. And better to say insertion sort in the worst case takes theta n square time, rather than saying insertion sort takes big O of n square in the worst case. Better to use theta notation, because when you know for sure that this is exactly n square, use theta notation. Also, if you want to talk about time complexity of insertion sort in one line, then you can say insertion sort is big O of n square. Here you can use big O notation, because when you say big O of n square, it covers the best case, covers the worst case. You are saying it is either n square or less than n square, which covers both the cases. Now, taking examples of theta notation. So all the constant values, they are theta 1, right? No other values. Theta means exact order of growth, right? So we can't have anything else like we had in big O and omega notations. We had sometimes unions of certain things, but we have exact sets here. So if you see this set, this has the leading term as linear, right? This is linear, log n is lower growing. This is also linear, so we can say it's theta n. Here, exact order of growth is n square. So we say all these things, this both things, they have theta n square order of growth. Theta n square means the highest growing term has to be n square, not more, not less. Let's now talk about analysis of some common loops that we see in programs. Let's take a look at this first example, the first simple loop. What we have here is, we have a loop that runs from I equal to 0, I smaller than I equal to I plus c. And n here is user input and c is a constant, some business constant, might be 2, 3 or anything. But n can have any value, it's not a constant, it's a user provided input. So if we see some examples, n equal to 10 and c equal to 2, how many times this loop runs? This runs for I equal to 0, then it runs for 2, 4, 6, 8, and when I becomes 10, we come out of the loop. So the loop runs 5 times. When n is 20 and I is 6, the loop runs 4 times. It runs for 0, 6, 12 and 18. Please pause this video and try to find out order of growth of this loop. You may assume that we are doing some constant work or theta 1 work inside the loop. We are not running another loop or we are not running any function call or anything. We are simply doing a constant amount of work. By looking at these examples, we can clearly see that this loop runs n by c ceiling times. For example, if n is 10 and this is 2, we have this loop running 5 times. For 20 and 6, we have this loop running 4 times, right? 20 by 6 is 3 point something. So ceiling of n by c times. And how do we write asymptotic notation for this? We ignore the constants, we ignore floor ceiling. Floor ceiling means plus minus 1 or something, right? So we can ignore those things and we can clearly say the time complexity of this part of the code is theta n. Let's now see our second example. Here we are running a loop from I equal to n and we run the loop while I is greater than 0 and we do I equal to I minus c. And inside this loop again we are doing some constant work. See, any work which is not dependent upon n, right, input is constant work, right? You might be printing something 10 times or 5 times, whatever you do, as long as it's not dependent upon input n, it's constant. So let's see the run of this loop for n equal to 10 and c equal to 2. It runs for 10, 8, 6, 4, 2 and when I becomes 0, we come out of the loop. For 20 and 6, it runs for 20, 14, 6 and 2 and then I becomes minus 4 and we come out of the loop. So it's again ceiling of n by c and you must have guessed the time complexity, it's theta n for this loop. Let's now see our third example. In this example, we are running a loop from I equal to 1, I smaller than n and I equal to I into c. Again, n is user input and c is a constant. For example, if you see for n equal to 33 and c equal to 2, it will run for 1, 2, 4, 8, 16, 32 and when I becomes 64, you will come out of the loop. For n equal to 81 and c equal to 3, it will run for 1, 3, 9 and when I becomes 81, you will come out of the loop. Please pause this video and try to guess time complexity or order of growth of this part of the code. If we take a closer look at these examples and maybe do some more examples, we can figure out that this loop runs log of base c and ceiling. For example, n is 33 and log in base 2 of 33 would be 5 point something, right? So it runs 6 times. This is 81. 81 base 3 would be 3, right? So it runs 3 times. We can show it mathematically also. See, this loop runs from I equal to 1, which can be written as c raised to the power 0. C raised to the power, any raised to the power 0 is 1, right? And say this loop runs k times, right? We need to figure out what is the value of k so that we can tell the order of growth. So k is going to, if this loop runs k times, then it's going to run from c raised to the power 0 to c raised to the power k minus 1. From 0 to k minus 1, we have k iterations, right? Now, for this loop to run these many times, this c raised to the power k minus 1 has to be smaller than n, right? And if I take log on both the sides, then I'll say k is smaller than log base c n plus 1. So from this also you can guess this loop is going to run theta log c n times. Let's now take a closer look at this fourth loop. In this loop we run from I equal to n, we run while I is greater than 1, and we do I equal to I by c. So for example, if n is 33, it's going to run for 33, then it's going to make it 16 because c is 2, then 8, then 4, then 2, right? For these inputs, it's going to run 5 times. For this input, it's going to run 3 times. Please pause this video and try to find out time complexity or order of growth. See, if you see these examples, or if you do more examples, you can clearly see that this loop actually runs floor of log n, right? It runs floor of log base cn. For example, if 33, you can notice that it's running 5 times. We'll get 5 point something when we do log of 33 base 2. 81 base 3 is clearly 3, so we have exact 3 times. So these many times this loop runs. Let's see mathematical understanding also. This loop begins with n divided by c raised to the power 0. C raised to the power 0 is 1. Then n divided by c, then n divided by c square. So this n divided by c means c raised to the power 1. Then if the loop runs k times, then this loop is going to run n by c raised to the power k minus 1, right? From 0 to k minus 1, total k times. Now this last term has to be greater than 1. For this last term to be greater than 1, we have c raised to the power k minus 1 is smaller than n. And if I take log both sides, I get this and then I get this. And this term has clear order of growth as log of n base c. Let's now see our fifth example, and this is the most complex example of all. So what are we doing here? We begin with I equal to 2, we run while I is smaller than n, and we do I equal to I raised to the power c. So I've written POW function here. If you're programming in C and C++, you can assume the same function which is present. But if you're programming in Java, you can use mat.power, right? So this function gives you the power, and we are doing some constant work inside the loop again. So if we see an example run for n equal to 33 and c equal to 2, we run for I equal to 2, then we run for 4, then we run for 16. So 2 raised to the power 2, 4, then 2 raised to the power 4 raised to the power 2 is 16. And after we do 16 raised to the power 2, we are going to get 256, which is way larger than 33. So we stop after 3 iterations. Let's see this example. We have n as 514 and we have c as 3. So we are running our loop for I equal to 2. Then we are running for 2 raised to the power 3, 8. Then we are running for 8 raised to the power 3, which is 512. And next time I will become 512 raised to the power 3, which is a huge number. So we'll stop after 3 iterations. And you can notice one interesting thing. Such a large number, 512, is reached only in 3 iterations. So the order of growth of this particular loop is very slow, right? It's going to be very low growing term. Please pause this video and try to guess order of growth of this particular part of the code. It's going to be smaller than log n also. The order of growth of this code is log n. Let's see how do we get log n. We run from I equal to 2. So we have 2 first. Then we do 2 raised to the power c. So we have 2 raised to the power c. Then we do 2 raised to the power c power c, right? So 2 raised to the power c power c. Then we keep on running this way and we have 2 raised to the power c power c power c and so on. Let's say this loop runs k times, right? Then I can write it as 2 raised to the power c raised to the power 0, right? Which is 1. 2 raised to the power 1 is 2 only, right? And I can write this as 2 raised to the power c raised to the power 1, which is 2 raised to the power c only. And this can be written as 2 raised to the power c square. And the last term, since this loop is going to run k times, is written as 2 raised to the power c raised to the power k minus 1. So the loop runs from 0 to k minus 1, total k times. Now this last term has to be smaller than n, right, from this condition. And if I take log on both sides, I can say c raised to the power k minus 1 is smaller than log of 2n. And if I take log again, I get k minus 1 is smaller than log c log 2n. Right, I move 1 on this side and get this expression, and this expression has clear order of growth as log n. So it's log n, which grows very slow. It's like almost like a constant. For such a big number, we did only 3 iterations, and in the 4th iteration we are going to get a number which is 512 raised to the power 3, which is a huge number. Also, when we talk about asymptotic time complexity in terms of log, the base does not matter. You can avoid writing the base, right? And you can simply write log n, because what happens in logs, you can change the base by multiplying with a constant, by using the simple log base change formula, and constants do not matter in asymptotic analysis. So we don't have to write base. Base does not matter as long as the base is constant. Let's now talk about analysis of multiple loops. So we are going to discuss different examples where we have more than one loop. So in this example, we have one loop after the other, and this way we have three loops. So the first loop runs from 0 to n minus 1, right, and does some constant work inside it. The second loop runs from 1 to n and does I equal to I into 2. Here we had I plus plus, here we have I equal to I into 2, and we do constant work inside it. The third loop runs from 1 to 99, right, and we do I plus plus inside this. Please pause this video and try to guess the time complexity of this whole function. The time complexity of first loop is theta n. We have discussed such loops. It is theta log n. We have discussed such loops also. And the time complexity of third loop is constant because the number of times it runs is not dependent upon n, right? It's a constant value. It's going to run 99 times, which is a constant value. So with theta, so we say theta 1. When you have one loop after the other, we simply add the time complexities. So overall time complexity is this much: theta n plus theta log n plus theta 1. And when you add three things, right, you always ignore the lower order terms or lower order growths. So you ignore these two and you say overall the time complexity is theta n. So this function has theta n time complexity. Let's now see our next example. In this example, we have nested loop. Nested loop means one loop inside the other loop. So we know what is the order of growth of this outer loop. It's theta n, right? We know this grows theta n times, right? And what is the order of growth of this inner loop? We have seen such loop also earlier. So it's theta log n, right? Now, what do we do to get the overall time? See, we have constant work going on inside it. So how many times this constant work will happen? It will happen theta n into theta log n times. When you have a nesting of loops, you simply multiply. When you have subsequent loops, you add. When you have nesting, you multiply, right? And you can guess it, right? It's going to run n times, and for every time, it's going to run log n times. So it has to be multiplied. If I add a printf statement, approximately these many times, n into log n times, this printf statement will print something, right? So the time complexity, the overall time complexity of this loop is going to be n log n, theta of n log n. Let's now see our third example, and this is mixed loop. We have nesting as well as subsequent loops. So we have already discussed order of growth of this part. It was theta n log n, right? We just discussed it. Now let's see this part. What is the order of growth of this part? This loop runs theta n times, and this loop also runs theta n times. So it's going to run theta n times for every iteration of outer loop. We simply multiply, that's why we get the order of growth as theta n square. So the overall growth is going to be addition of these two because this nested loop is after this loop, right? Now we use the subsequent thing. And if I add these two terms, n log n with n square, you can clearly see n square is a higher order growing term. So we are going to have overall time complexity as theta n square. Theta n square is the time complexity of this whole function. It's theta n log n plus theta n square. We ignored the lower order term and we got this. Let's now see our last function. In this function, we have two different inputs. We have n and m. Please pause this video and try to guess order of growth of this function. So we have already seen order of growth of this part is theta n log n, right? This is just something we just saw. It's n log n. Now order of growth of this part, the bottom part is going to be theta of m square. You must have guessed it, right? We're running it as theta m times, then we have another loop which also runs theta m times. So the overall time is going to be theta of n log n plus theta of m square. See, n and m are different inputs. So we can't ignore n log n and just consider m square because they are different inputs. M might be a very small value, n might be a very large value. So we say overall time complexity is theta of n log n plus m square. We can take these terms inside theta notation and we can write this as the time complexity of this function. There are many real-world examples of algorithms that take multiple inputs. For example, graph algorithms. For graph algorithms, we many times analyze the algorithms for vertices and edges. How much is the time complexity in terms of vertices and edges? Another example can be, say you want to merge two arrays. one array is of size n and another array is of size m, and these are sorted arrays and you want to merge them in sorted ways. It's a popular question. So the time complexity of its solution is also going to be in terms of two inputs, n and m. Let us talk about analysis of recursive codes. So far we have talked about analysis of iterative codes. In recursive codes, what happens is a function calls itself. For example, here I have written a function fun that takes an integer value n. It returns immediately if n is smaller or equal to 0. In other cases, it prints GFG on the screen and then it calls itself for n by 2 and n by 2, right? So we need to know how much time this function takes, and it's not that easy. For iterative solutions, we just had to count how many operations we are doing in terms of input size. Here we do not have any loop sort of thing, or we do not have any way to count, direct way to count how many operations we are doing. So what we do to solve recursive solutions is we first write a recurrence relation. That's what we are going to learn in this video. So first we will learn how to write the recurrence relation in this video, and in the next video we will discuss how do we solve the recurrence relations. So how do we write recurrence relation for this? What we do is we assume that this function takes tn time for input value n, right? And then this function is making two recursive calls. So it's going to take tn by 2, right, plus tn by 2 by these two recursive calls. If it takes n time for input size n, then it's going to take tn by 2 here. Now, apart from these two calls, it's also doing something more, and all that work it is doing, it's constant amount of work. It's not doing any loop, it's not making any function call, right? So it's constant amount of work. So we can say theta 1, right? So this relation is true when n is greater than 0, right? And when n is smaller than or equal to 0, right, then what we have? We have tn equal to theta 1. It's a constant amount of work, because if that is the case, then we just return, right? So this is our general case, and this is our base case, and this can be rewritten as 2tn by 2 plus theta 1, right? That's what we can rewrite. I just added those two terms. And if n is to be considered as a positive value, then you can simply write that it's going to reach ultimately the value 0, and t0 is theta 1, right? That's our corner case or base case to solve the problem when n is greater than 0. So this is how we write the recurrence relation. This is our recurrence relation. This is our base case for recurrence relation. In the next video, we'll discuss how do we solve these recurrence relations. Here is an exercise for you. Please pause this video and try to write down recurrence relation for this function. So in this function, what is happening? Say if this function takes tn time, then we are doing tn by 2 work here, right? And all this is true when n is greater than 0, plus tn by 3 work here in the next call, and then we are doing this theta n work, right? So the recurrence relation is this when n is greater than 0. And when n becomes 0, or when n is smaller than or equal to 0, how much work we are doing? We are doing constant amount of work. So we can write t0 is theta 1, right? So that's the time complexity of, that's the recurrence relation for time complexity computation of this recursive function. Here is last exercise for you. Please take a closer look at this recursive function and try to guess the recurrence relation for this. And it's super easy. If this function takes tn time, then it's going to take tn minus 1 the recursive call, then it's going to take theta 1 work for all this condition check and printing, right? And when n is 1, then it's going to take theta 1 time. So this is the recurrence relation. Let's now talk about solving recurrences. So we are given a recurrence relation like this. We need to find the value of tn. There are multiple methods to solve recurrences, like there is master method, which requires us to remember a formula and works only for a particular form. In this video, we are going to talk about recursion tree method, which is a general purpose method, does not require us to remember any formula. However, in some cases, this recursion tree method does not give you the exact bound, gives you an upper bound. And this method is very close to programmers. As a programmer, we most of the time draw the recursion tree and we feel comfortable writing the recursion tree. So what we do in this method is we draw the recursion tree, and in the recursion tree nodes, we write down the amount of work done in every function call, right? And at the end, we compute the total work done in the whole recursion tree. So say if I have drawn this complete recursion tree, I just need to count the sum of all node values. So what we do to compute the sum of all node values, we compute the sum of this level, then this level, then this level, and we find the pattern and we find sum of whole series. That's what we do in the recursion tree method. How do we draw this recursion tree? So these are the steps. So if you see the recurrence relation that I have here, we have a recursive part here, right? There are two recursive calls, and then we have a non-recursive part. This is non-recursive part and this is recursive part, right? So what we do is we write the non-recursive part as root of the tree first. Then we write the two recursive calls. There are two recursive calls here, that's why I've written two. If there were three, we would have written three. If there was one, we would have written one. Then there are two recursive calls, so we write those two children here. Then once we have drawn this recursion tree, we further expand these calls, right? And how do we expand it? This is the recursive call for Tn by 2, right? Tn by 2 means it's going to have 2Tn by 4 plus Cn by 2. If I put n equal to n by 2, I'll get 2Tn by 4 plus Cn by 2. So in that, the non-recursive part is Cn by 2. So I write Cn by 2 and I write the recursive parts here. Then Cn by 2 and recursive parts here. See, we need to compute the total work done. How much work we are doing here? Cn. And how much work we are doing here? Cn by 2 plus Cn by 2, which is Cn. You might have guessed the pattern now, right? As soon as you find a pattern, you guess the pattern, you can stop drawing the recursion tree. I have drawn one more time for more clarity. So next time we are going to have Cn by 4, Cn by 4, Cn by 4, and you have 4 Cn by 4, so you have total work done again as Cn. And at the bottom level, you will have C, and you will again have Cn. So you are doing Cn work at every level. We just need to find out how many terms the series has, and we just need to add Cn those many times. So the total work done in this recursion tree is Cn plus Cn plus Cn, and the last term is also Cn, right? Now we just need to find out how many terms we have. So what is the height of this binary tree? Can you find an expression for height? You can take some examples. For example, if n is 14, what will happen? You will have 14, then you will have a child with value 7, then 3, then 1, right? So how many levels we have? 1, 2, 3, 4 for 14. And how many levels we will have for 15? Again 4. For 16, we will have 5 levels. So it's coming out to be around log n. And when we talk about asymptotic analysis, we do not care generally about 1 plus minus, right? As long as we know order of growth is log n, we consider log n. And if we just want to find out the exact value, see, let's do one more example, 4, 2 and 1. So how many terms we have for 16? We have 5. It's mainly floor of log 2n, right, and plus 1. Those many terms we are going to have in the series. So if n is 14, then floor is of log 2 base n is 3, and 3 plus 1 is 4. If it's 16, then we have floor as 4 and we have plus 1, 5. So that's the number of terms, and you can write it as theta log n, right? We don't need to care about floor, ceil and plus minus. So we have theta log n terms, right, in total, and every term is having value Cn, right? So how much is the sum of this whole series? It's clearly theta of n log n. So that's the amount of work we are doing in this recursion tree, and that's the value of this recurrence. That's the asymptotic value of this recurrence, right? We haven't found the exact value, we have found the asymptotic value. Now one more thing, I have written a very simple recurrence relation for simplicity, and this recurrence relation kind of belongs to merge sort, right? In merge sort, we make two recursive calls and then we do merge procedure, which takes theta n time. In practice, you might have C1n plus C2, and these C also might not be same, right? This might be, say, C1, right? C1n, and this might be C2, right? Because in the base case, you will have different amount of work, and in the other cases, you will have different amount of constant work, or you will have different constants here and there, right? So, but if you consider even C1, C2, and if you just rewrite these expressions, say we have C1n, C1n, till the C1n, C1n, C1n till the last term, at the end we have C2n, right? Let's say we have C2n. This is also going to be turning out to be theta n log n. You can notice, right? How many terms do we have? Floor of log n. right? Total terms are floor of log n plus 1, but if I do not consider the last level, then I have total floor of log n terms, right? And how much work I am doing at every level? I am doing C1n into floor of log n. I can say theta log n, right? Floor ceiling we can ignore. Plus I am doing at the last level, how much work I am doing? Plus C2n. And this is a lower order term. When we talk about asymptotic analysis, we can ignore the lower order term. So we can again say it's theta of n log n. For simplicity only, I considered C1 and C2 both, but when you analyze the actual algorithms, they would be having different values. Let's now solve more recurrences using recursion tree method. Please take a closer look at this recurrence, pause this video and try to find the value of Tn yourself using recursion tree method. So here I have written the solution. So what we do in the recursion tree method is the first step. We write the non-recursive part as root and then we write the recursive parts as children, right? We write C and Tn minus 1, Tn minus 1. Then we again do the same thing. We write the non-recursive part as root and write the children Tn minus 2, Tn minus 2. Non-recursive part as root and write the children. Then we again do the same thing for this. And while we are doing this, we keep checking what are the values of work done at every level. At this level, we are doing C work. At this level, we are doing 2C work. At the next level, we are going to do 4C work, right? So we don't need to break it further because you must have guessed the pattern now, right? It's C work, it's 2C, then 4C, and at the next level, you are going to have 8C. And how many levels we are going to have? See, the series is very clear. It's the series of total work done. The value of the total work done is C plus 2C plus 4C and what will be the last term and how many terms we are going to have. See, if n is 3, then you will have 3 is called, then 2 is called, then 1 is called. You are going to have 3 levels. So for any value of n, you are going to have n levels, right? For n equal to 4, you are going to have 4 levels in the recursion tree. So the number of terms in this series is going to be n, and it's a geometric progression clearly with a common ratio as 2. So we can simply apply the formula of geometric progression, right? We can take the C out, right? And we can write the series as 1 plus 2 plus 4 and till n terms. And this value is, the formula for geometric series is a into r raised to the power n. So 2 raised to the power n, r is common ratio, minus 1 divided by 2 minus 1. So this is the value we get, and this is clearly theta of 2 raised to the power n, right? Rest of the things are constant, and that's the value of this expression, and that's the value of Tn. And this recurrence you find in Tower of Hanoi problem. In the Tower of Hanoi problem that we have discussed in the recursion here, what we do in the Tower of Hanoi, we first recursively call for n minus 1, then we recursively call for again n minus 1, and we do constant extra work. So that's the expression we get, and we get this value. And again, these C would be different in actual scenario. They would be C1 and C2, but you will get the same value as the value of this recurrence. Here is one more exercise for you. Please take a closer look at this recurrence, pause this video, use the recursion tree method and find the value of Tn. Here is the recursion tree method solution. We first write the non-recursive part as the root. There is only one recursive call, so we write one child. Then we again break it further, non-recursive part as root and its child. Now we see a pattern. We are doing C work here, C work here, and C work at the next level also, and C work is going to happen at the last level also. We just need to find out how many levels we have. And we've discussed one such example earlier, right? When you divide n by 2, in such cases, we have log of n base 2 floor plus 1 levels. And we are going to have these many C's. So what is the summation of the series? It's clearly theta of log n, right? So that's the time complexity of this recurrence. And this recurrence you would see in binary search. In binary search, what we do is, we recursively call either for the left half or for the right half, and we do additional constant work. Now here is third example for you. Please take a closer look at this recurrence. I have 2 Tn by 2 now. Earlier I had Tn by 2. Pause this video, use the recursion tree method and find the value of Tn. Here is recursion tree solution for this recurrence. What I have done here is, I have first written the non-recursive part, then I have written the recursive parts. So this, we are doing C work here, then I have further broken it down, non-recursive parts and then recursive parts. 2C work I am doing here, then I am doing 4C work. So I see a pattern, right? I see that it's C, 2C, 4C, and it's going to be 8C. So I just need to figure out how many terms are going to be there in the series. So how many terms we are going to have? We have discussed this earlier. We are going to have log of floor of 2n plus 1 terms, right? And I can write these terms as theta of log 2n. I can simply take log 2n terms, right? Because 1 plus minus floor ceiling do not matter when we talk about asymptotic analysis. So these many terms we have, and if I find out the sum of this series for log 2n terms, it's r raised to the power n, common ratio r is 2, and n is those many terms log 2n, right? Minus 1, r minus 1. So if you see 2 raised to the power log 2, this 2 and 2 are common. So in those cases, we can write this expression as n. So it's n minus 1 divided by 2 minus 1, which is theta n. So the time complexity of this recurrence relation is theta n. In all the examples that we have discussed so far, we could find exact bound. We could find theta notation for the recurrences. There might be certain situations where it might not be possible to find the exact bound. And here is one example. Let's say we have this recurrence relation, Tn equal to Tn by 4 plus Tn by 2 plus Cn, and T1 is C. So if I break this using a normal recursion tree method, what will happen? I'll write the non-recursive part, then I'll write the recursive parts. Then I'll break it further. Non-recursive part of this is going to be Cn by 4. This is going to be Cn by 2. Then Tn by 16, Tn by 8, Tn by 8 and Tn by 4. And if I do the sum of these terms, I'll get 3Cn by 4 here and Cn here. Now, if I do the sum of these 4 terms, I am going to get Cn by 16 plus Cn by 8 plus Cn by 8 plus Cn by 4. So this sum of these two is going to be Cn by 4, right? And sum of Cn by 4 plus Cn by 4 is going to be Cn by 2. And Cn by 16 plus Cn by 2 is going to be 9 Cn by 16, right? You might see a pattern now. It's a geometric progression with common ratio as 3 by 4, right? Cn, 3 Cn by 4, 9 Cn by 16. Now the problem here is all the leaves, they are not going to be at the same level. That's why this is special. That's why I said we are going to find an upper bound, right? So it's not going to be exact geometric progression till the bottom, right? It's going to be geometric progression up to certain points. Then this node will exhaust or finish first. You will see a leaf node very early here, and you will see a leaf node very late here in the last side, right? Why? Because we are reducing it by 4 here, 4, 16, then 64, and here we are reducing by 2. So 2, 4, 8, 16, right? And you will see somewhere in the middle here in the leaves. So here the leaf is going to be the topmost leaf, and it's going to be the bottommost leaf. It's going to be something like a tree where you have this at the very early and this at very late, and somewhere in the middle subtrees. So how do we find the exact bound? See, it's very, very difficult to find the exact bound. So what we do, we assume that the tree is full. We say we don't assume that there are we don't find the exact bound, right? We assume that the tree is full, and using this assumption we find a value and we say it's an upper bound, right? Because we are considering the tree to be full and we are calculating that value, and the actual value would be less than that because we are doing somewhere less work than this. So that's what I meant by upper bound. So what I do is I consider this geometric progression, right? The geometric progression is Cn plus 3Cn by 4 plus 9Cn by 16, right? And it's going to be go on like this. If I consider this tree as full, then how many terms the series would have? Basically, we need to find the depth of the rightmost leaf, right? And this is going to be reducing by 2, n equal to n by 2, n by 4 and so on. And we know the number of terms for that. It's theta of log n, right? We've done it multiple times. So there are theta log n terms in this series, right? And this series is a geometric progression. And the common ratio of this geometric progression is 3 by 4, right? It's less than 1. So one way is we find the exact value of this using the formula 1 minus r raised to the power n divided by 1 minus r. It's going to be complicated, right? What we can do is, we are anyways finding an upper bound, right? We can use big O and we can find the sum of infinite series. Because sum of infinite series with a common ratio less than 1 is very simple. It's a upon 1 minus r. So we are going to have Cn upon 1 minus 3 by 4, right? And this turns out to be big O of n only, right? Because these are just constants. So an upper bound on this recurrence is big O of n, right? So we could use recursion tree method to find an upper bound, and it's a good upper bound, right? Not bad upper bound, not like n square or n cube. We could find big O of n linear time upper bound on this recurrence relation. Here is one more example. We are going to use recursion tree method to find an upper bound. See, whenever you see a recurrence where one term is changing at a different speed and the other term is changing at a different speed, then you can get upper bound only using recursion tree method, right? Because doing exact computations might be difficult. So why are we getting upper bound here? See, if you draw the recursion tree of this, what will happen? It's changing, it's being reduced 1, 1, 1 at a time. It's reduced 2, 2, 2 at a time. So you will have a tree like this where this will be finished very fast. So you will have a tree where this leaf will be coming very early and this leaf will be coming very late, right? A tree like this you will have, right? So it will not be like a tree where every leaf is at the same level. This leaf is very high and this leaf is very low, right? So we can't find the exact bound, right? We can't do the exact sum here. We need, if we do, we need lots of more mathematics. It's difficult. So what are we going to do? We are going to consider this as a perfect tree and we are going to find an upper bound. So pause this video now and find an upper bound. So here is solution using recursion tree method. We have first written the non-recursive part, then recursive parts, then again non-recursive part and recursive parts, and then we did it again and we found the pattern that it's a geometric progression with common ratio 2. We are doing C work here, 2C here, 4C here, right? But the point is, it's not going to be a full tree. It's not going to be a geometric progression after certain terms. What will happen? This will finish very early and then you will have variations from the geometric progression, right? It won't be exact geometric progression, right? So it might happen after certain terms. It's not the double, right? It's less than double, then more less than double, and then it finishes slowly, right? So something like this is going to happen. So what we do here is we find an upper bound. We don't do the exact mathematics. We find an upper bound. We consider this as a full tree, right? And we say, okay, we can't do the exact analysis because it requires too much mathematics. We give you an upper bound. That's what recursion tree method claims. So what we do is we consider all n terms. We consider this geometric progression and put a big O notation here, right? Big O our friend, right? Whenever you don't know the exact bound, you use big O notation. And we have already discussed some of the series for n terms. It turns out to be 2 raised to the power n. Although in the earlier example, we used theta notation. Now we are using big O notation because it's an upper bound, right? We have used big O here. So we are using big O here as well. In this video, we are going to talk about space complexity of algorithms or programs. Space complexity is defined as order of growth of memory space or RAM space in terms of input size. It's similar to time complexity. Time complexity is order of growth of time taken of an algorithm or program in terms of input size. Instead of time taken, here we have memory taken or RAM amount taken. Let's take a look at these two programs to get an idea. This program takes how much space in terms of input size? Only constant amount of space. You have some constant number of variables n. There's in fact only one variable n. So the amount of memory space does not grow in terms of input size. If you have n equal to 1000, then only you are going to have only one variable in this program n, right? And as long as the number of variables are constant, it's not an array of variables or array of memory. It's considered as constant when we talk about space complexity. Let's see this program. It's another way to find sum of first 10 natural numbers. It's a way to do direct formula and it's a way to add the numbers one by one. Can you guess the space complexity of this program? How many variables we need in terms of input n? Say if n is 1000, how many variables you need? Sum, I, right? And then 3 variables. And then if n is 10,000, then also you need 3 variables. Sum, I and n. So the space complexity of this program is also big O of 1 or theta of 1. Please note that we represent space complexity also using same asymptotic notations as we do for time complexity. So space complexity of these both programs is theta 1, theta 1. Or you can say big O1. They both represent constant order of growth. But we cannot use omega 1, right? Omega 1 means its minimum constant, might be higher. So theta 1 and big O1, they give proper information that it's always going to be constant, not more than that. Let us take a look at this function. In this function, we are receiving an array as an input, size of array as an input, and what we do, we run a loop to find sum of elements in the array, right? We traverse through all the array elements, do the sum, and then return the sum. Now, what is the space complexity of this program? If you talk about input size n, if n is 1000, then how big your array is going to be? 1000 size. If n is 10,000, then your array is going to be of size 10,000. So the space complexity of this program is theta n. It's always going to need theta n space in terms of input size. The space grows linearly in terms of input side, and that's what is the exact growth. Right? It's not an upper bound or lower bound. We know exactly that it's going to grow theta n in terms of input size. So we use theta notation to represent the exact growth. Let us now define one more term, auxiliary space. This is the term we use most of the time. We use it more than space complexity. Auxiliary space is order of growth of extra space or temporary space that you create to solve a problem or to write a code for a given problem. If you take a look at this array sum function, what it does, it takes an input array, finds the sum of elements in the array. So space complexity of this program is clearly theta n. We have talked about it because the space required for this program, the RAM space required for this program is going to grow linearly in terms of input size. But if you talk about extra space, space created for memory other than input output, how much extra space this program needs? It needs linear space only for input. It does not use any extra array to do any computations. So auxiliary space for this program is theta 1, but space complexity of this program is theta n. Auxiliary space theta 1, space complexity theta n. When we talk about array problems, or list problems or any problems which use an input container, they're anyways going to need theta n space. Their space complexity is going to be at least theta n. And if you use an array or an extra array of size n, the space complexity is going to remain theta n. So rather than space complexity, we care about auxiliary space. For example, when we study sorting algorithms, there are some sorting algorithms which do not use extra array to do the sorting, like insertion sort, bubble sort, selection sort. However, there exist sorting algorithms that use extra space to do the sorting, extra array to do the sorting. For example, merge sort. Merge sort is a sorting algorithm that uses an extra array of size n to sort an array. If you take a look at all the sorting algorithms, they are all theta n space complexity because they are all need an array to sort, right? But we cannot compare them in terms of space complexity because they are all theta n. So we compare them in terms of auxiliary space. How much auxiliary space a sorting algorithm requires? We say insertion sort, selection sort, bubble sort, heap sort, they are all theta 1 auxiliary space. Merge sort is theta n auxiliary space. Quick sort is theta log n auxiliary space in best case because quick sort has recursion. We'll talk about some recursion space complexities as well in this same video. So space complexity is less used and auxiliary space is more used because it gives you more information. So space complexity is a less used term compared to auxiliary space because if you're talking about array, list, you need space complexity theta n to process them. But you can compare algorithms by auxiliary space. You can decide which is better by taking a look at the auxiliary space they require. Let us take a look at this recursive program to find sum of first n natural numbers. How does this program work? It takes an input n. If n becomes 0 or less than 0, it returns 0 as sum of natural numbers. And if n is something positive, it adds n and calls for fun n minus 1. So how does this work? Fun 5 calls fun 4, fun 4 calls fun 3, fun 3 calls fun 2, fun 2 calls fun 1, and then fun 1 calls fun 0. Right? And what fun 0 returns? It returns 0 to its parent. Right? Then what parent does? It takes this 0 and adds to n. And what is n for the parent? Parent has n as 1. So it returns 1 plus 0, 1 to its parent. Then this returns n, which is 2 for this function call. 2 plus 1, 3 to its parent. And then it returns 3 plus 3, 6 to its parent. Then it returns 6 plus 4, 10 to its parent. And this function returns 10 plus 5, 15 to the caller. So we get the value 15 returned from this function call. So this is how this recursive function works to do sum of n natural numbers. Now what is the space complexity of this program or auxiliary space required for this program? If you take a look at this, you are not using any array or a list or any other data type like hash table or anything to store any extra variable, but this program does not have theta 1 space complexity or theta 1 auxiliary space. This program needs extra space. This program needs extra space to store these function calls in a function call stack. So how do these function calls work? You have fun5 initially in the function call stack, then fun5 calls fun4, and fun5 is waiting here for fun4 to finish, then only fun5 can resume. So fun5's state is stored in the function call stack, then fun4's state is stored, then fun3's function state is stored, and none of these functions can finish until fun0 has finished. Once fun0 finishes, it returns control back to the caller, then caller finishes, then caller of the caller finishes, then parent of it, then parent of it. So that's how these function calls happen. Now there is a movement when you have n plus 1 function call stacks, function calls states stored in the function call stack, right? At a movement, in the worst case, what will happen? Fun5 will be there in the function call stack when fun0 is called. This will happen when fun0 is being executed. You will have fun4, then you will have fun3, then you will have fun2, then you will have fun1, and then you will have fun0. So you need to have space for 6 function calls. N plus 1 is the extra space required in the worst case. There is a movement when you have n plus 1 function calls stored in the function call stack, right? N plus 1 functions activation record stored in the function call stack. So the space complexity required for this program is theta n. N plus 1 can be written as theta n. And you can also say auxiliary space for this program is also theta n. Let us do an exercise considering different solutions of Fibonacci number. Let us find out space complexity and auxiliary space for all these solutions. The first solution that I am going to consider is simple recursive solution for Fibonacci numbers. Please pause this video, draw the recursion tree of Fibonacci numbers and try to guess the space complexity and auxiliary space for this program. They are going to be same for this. Before we talk about auxiliary space or space complexity, let me clarify the problem more, the solution more. So we are talking about Fibonacci numbers where nth Fibonacci number is defined as sum of n minus 1th Fibonacci number and n minus 2th Fibonacci number. This is 0th Fibonacci number for n equal to 0. This is for n equal to 1. We expect the output as 1. For n equal to 2, we simply do a sum of these two and we get 0 plus 1, 1. So this is for n equal to 2. For n equal to 3, we do a sum of recursive calls for Fibonacci 2 and Fibonacci 1 and we get 2, right? That's what we are doing here. And we are handling the base cases. If n becomes 0 or 1, we return n. For 0, it's 0. For 1, it's 1. I have also drawn the recursion tree for Fibonacci numbers. let's now understand the extra space this program is going to take. I just want to give you a simple formula to find out auxiliary space required for any recursion. It's always equal to the height of this tree, maximum length of root to leaf path. So you can see maximum length of root to leaf path here is 4, right? And that's what auxiliary space and space complexity is for Fibonacci numbers, and we can always find out this way. So we can say that auxiliary space required for n equal to 4 is of order 4, which means it grows linearly in terms of time. So that's a direct way to figure out. We can say that auxiliary space for required this recursive Fibonacci number is theta n. Let's now understand how am I defining this formula that it's equal to the maximum height of recursion tree. What happens when you call it recursively? You call it for Fibonacci 4, and Fibonacci 4 begins its execution from here, comes here, and then makes a recursive call for Fibonacci 3, right? So what do you have in the recursion call stack as of now? You have Fibonacci 4, then Fibonacci 3 goes into the recursion call stack. So you are here, then you came here. Now Fibonacci 3 also begins its execution from here and comes to Fibonacci 2, right? Calls for Fibonacci 2. So Fibonacci 2 also goes into the recursion call stack. So you called for this as well. Now Fibonacci 2 again begins its execution, does not go into the base cases, calls for Fibonacci 1, right? So Fibonacci 1 also goes into the recursion call stack. Now Fibonacci 1, it begins its execution from here, goes into the base case and returns 1 immediately to the parent. So 1 is returned to the parent. And Fibonacci 1 has finished at this point. It does not make recursive calls. So Fibonacci 1 is done. It goes out of the recursion call stack. Now control goes back to Fibonacci 2, and what Fibonacci 2 does, it has already done with the Fibonacci 1. Now it calls for Fibonacci 0. So Fibonacci 0 goes into the recursion call stack. And you can notice that before Fibonacci 0 was called, all these height things of the recursion call, they were there in the recursion call stack. Now this path is there in the recursion call stack. So at any moment, the number of function calls you have in the recursion call stack is paths from root to leaves. So one moment you have these many function calls, then you have these many function calls, then you have these many function calls, then you have these many function calls, and then you have these many function calls. So Fibonacci 0 begins its execution, goes into the base case and returns immediately, and it goes out of the recursion call stack as well. So Fibonacci 0 is not here now, and it returns 0 to its parent. And what parent call does? It does 1 plus 0, 1, and gives the control back to its parent. Now parent, which was waiting for here, now makes a recursive call for Fibonacci 1. So Fibonacci 1 begins its execution, it goes into the recursion call stack. Fibonacci 2 also goes out of the recursion call stack, right? Because Fibonacci 2 was finished when these two were called. Now Fibonacci 1 goes into the recursion call stack. Because Fibonacci 4 has made a call for the right side. So this is the new recursion tree path from root to a leaf. Now Fibonacci 1 finishes its execution because it's in the base case and returns the value 1 to its parent, right? So Fibonacci 1 goes out of the recursion call stack. Now parent also is done because fun 2 is over, fun 1 is over. And what does it return? It returns 1 plus 1, 2 to its parent. So for Fibonacci 3 also goes out of the recursion call stack. Then control comes to Fibonacci 4, which was waiting for Fibonacci 3 to finish. Fibonacci 3 has finished, and now it's going to call Fibonacci 2. And Fibonacci 2 is going to call Fibonacci 1. So you can see now you have the next path in the recursion call stack. Fibonacci 1 finishes its execution, goes into the base case, right? Returns 1 to the parent call. And then it calls, Fibonacci 2 calls Fibonacci 0. Fibonacci 0 also finishes. So Fibonacci 0 also goes into the recursion call stack before being finished, right? So you again have this path in the recursion call stack. And then Fibonacci 0 goes into the base case and finishes. Now the parent gets the control back, returns 1 plus 0, 1 to its parent. And this Fibonacci 4 returns 2 plus 1, 3 to the parent call. So we get 3 as an output. At any moment, we never required more than height of this recursion call stack space in memory. That's why we say auxiliary space or space complexity required for this program is theta n. Let us now take a look at another solution to find nth Fibonacci number. What I've done here is I've created an array of size n plus 1 and I call this array as f. For n equal to 4, I'll create an array of size 5 with indexes 0, 1, 2, 3, 4. And then I'm initializing the first two Fibonacci numbers as 0 and 1. So this is initialized as 0 and this is initialized as 1. Now I run a loop for I equal to 2 to I equal to n and I plus plus, and what do I do in this loop? I use the same recursive formula. So this becomes I minus 1 plus I minus 2, so it becomes 1. This becomes I minus 1 plus I minus 2, so it becomes 2. And this becomes 1 plus 2, 3. So that's how we compute the Fibonacci numbers now. And we return the result as 2, or return the result as 3. Now what do you say about space complexity and auxiliary space for this program? Please pause this video and try to guess the solution yourself. Both space complexity and auxiliary space are theta n here. We need n plus 1 space for this auxiliary space. See, we can always ignore the extra 1 or 2 or 3 or 100 constants, right? As long as they are constant number of constants. We only need to consider auxiliary space which grows in terms of input size, right? So this is the array which is dependent upon n, right? If n is 1000, this array is going to be size 1001. If n has 1 lakh, then it's going to be 1 lakh plus 1. So this array grows in terms of input size. So auxiliary space required for this program or this function is theta n. Same as space complexity. Space complexity is also theta n. Let us now take a look at this another solution to find the nth Fibonacci number. The idea here is to optimize the previous solution in terms of space. If we see the previous solution, to find the ith value in fi, we were only using fi minus 1 and fi minus 2. So instead of creating the whole array of size n, we can just store the previous two Fibonacci numbers in two variables, right? So I created two variables a and b here, which store the previous two Fibonacci numbers, and I store the current Fibonacci number in c. Initially, a is 0 and b is 1. So let's do a dry run of this for n equal to 4. What happens? You do not go into the base cases, we have handled them explicitly. Then we come for I equal to 2 and we run this loop. What do? We make c equal to 0 plus 1. We make a equal to b. So a becomes 1 and b becomes 1. b is equal to c. So you can see that before going to the next two Fibonacci number, before computing the next Fibonacci number, we have the previous two Fibonacci numbers, right? A is 1 and b is 1. So next Fibonacci number can be easily computed as a plus b. That's what we do in the iteration for I equal to 3. Right, we make c equal to 2 and then we update a and b accordingly for the next iteration. We update a as b, so a has the second previous Fibonacci number for next iteration and b has the previous Fibonacci number, right? So b is equal to c by the end of this loop, right? So when you begin next time, you have the previous two Fibonacci numbers here. Now you compute the current Fibonacci number, then you update the previous to previous Fibonacci number, then you update the previous Fibonacci number. That's how you get nth Fibonacci number at the end and you return it. This particular solution, how much space it requires, how much auxiliary space and what is the space complexity? You are only using a constant number of variables. A, B, C, I. Number of these variables is not dependent upon the n. The auxiliary space required is not dependent upon the n. So space complexity and auxiliary space both are theta 1 here. Both are theta 1 in this example.
So we did in space optimization in the previous solution, and we got the solution which works in theta1 space, and same time taken by the previous solution was also theta n, time taken by this solution is also theta n.